Something strange is happening near Jupiter, something scientists have been searching for more than a century, without ever expecting to see it happening this close to home. It isn't a new storm. It isn't a new moon. And it isn't just another beautiful photograph. A spacecraft roughly the size of a basketball court has been circling Jupiter, moving through one of the most extreme magnetic environments in the solar system. And during one of those encounters, it detected particles traveling at astonishing speeds, nearly approaching the speed of light. Then researchers compared what they were seeing near Jupiter with the particle acceleration associated with some of the most violent explosions in the universe. The pattern was striking. A process happening near a planet in our own solar system appears to follow the same basic physics that may operate around enormous stellar explosions. And if that connection holds, Jupiter may be giving scientists something they have wanted for generations: a nearby laboratory for studying how the universe creates cosmic rays. For more than 100 years, physicists have been trying to answer one enormous question. Where do the universe's most energetic particles actually come from? Cosmic rays constantly bombard Earth. Scientists have detected and measured them for generations. Some are produced by the Sun. Others are associated with supernova remnants, the expanding debris left behind when massive stars explode. But knowing where cosmic rays might come from is not the same as understanding exactly how they are accelerated. What physical mechanism can take an ordinary charged particle and push it toward incredible speeds? For decades, much of the answer existed mainly in theory. Scientists had mathematical models. They had indirect evidence. They had observations from distant objects. But they rarely had the opportunity to watch the acceleration process happening up close. That changed when NASA's Juno spacecraft passed through Jupiter's enormous foreshock region. And the story begins not on Jupiter itself, but in the space directly in front of it. The solar system isn't empty. The Sun constantly releases a stream of charged particles called the solar wind. As that material races outward, it encounters the magnetic field surrounding planets. When the solar wind crashes into a planetary magnetic field, it creates a shock wave called a bow shock. Imagine a boat moving through water. The boat pushes the water aside and creates a disturbance in front of it. Now replace the boat with a planet-sized magnetic field and replace the water with charged plasma. That is roughly what happens around a planet like Jupiter. Just ahead of the bow shock is a turbulent region called the foreshock. Here, magnetic fields and charged particles interact in complicated ways. Some particles can become trapped, reflected, and accelerated to extremely high energies. Earth has a foreshock. Jupiter has one too. But Jupiter's version is vastly larger. Its magnetic environment is so enormous that it provides scientists with a natural particle accelerator on a planetary scale. And this is where Juno enters the story. NASA's Juno spacecraft has been orbiting Jupiter since 2016. During its mission, it has repeatedly passed through the planet's extreme magnetic environment, collecting measurements that no telescope on Earth could obtain. Juno detected energetic electrons in Jupiter's foreshock region. That was already fascinating. But researchers didn't stop at measuring the particles. They looked for a relationship. When they compared particle acceleration near Jupiter with observations from Earth's magnetosphere and with theoretical expectations for much larger astrophysical shock waves, they found a striking scaling pattern. As the characteristic size of the shock environment increases, the particles can reach higher energies. And that matters because much larger magnetic shock environments exist around supernova remnants. Those remnants have long been considered possible cosmic ray factories. The problem was that scientists couldn't simply fly a spacecraft into a supernova remnant and watch the acceleration process from inside. Jupiter gives them something much more practical: a nearby natural laboratory. Think about how extraordinary that is. A spacecraft operating hundreds of millions of kilometers from Earth can study a process happening near Jupiter, and those measurements can help scientists test ideas about explosions occurring across the galaxy. Jupiter isn't a supernova. Its environment is nowhere near as energetic. But the underlying physics may be similar. That distinction is important. The discovery doesn't mean scientists have suddenly solved every mystery surrounding cosmic rays. It means they now have stronger local evidence that a particular acceleration mechanism can work and that its behavior scales in a way consistent with what scientists expect from much larger environments. And that is a huge step. Earlier missions, including NASA's magnetospheric multiscale mission and Themis, had already shown that energetic particles can appear in Earth's foreshock. But Earth is a relatively small magnetic obstacle. Jupiter is on an entirely different scale. If the same physics operates there, the accelerated particles should reach much greater energies. That was the prediction. And this time, nature appears to have followed the prediction remarkably well. Jupiter's enormous bow shock is created by its gigantic magnetic environment interacting with the solar wind. The result is a natural accelerator operating continuously in space. No engineers built it. No power cables feed it. No laboratory created it. The planet simply does it. And that is what makes Jupiter so valuable to astrophysicists. It allows scientists to study extreme plasma physics without needing to travel to a supernova. But Jupiter's surprises don't stop with cosmic rays. The planet itself has been forcing scientists to rethink some of the most basic assumptions they had about it. Recent Juno measurements have refined our understanding of Jupiter's size and shape. For decades, scientists relied heavily on measurements from earlier missions, including Pioneer and Voyager. Juno's modern instruments can make far more precise measurements of Jupiter's gravity, atmosphere, and surrounding environment. Even small corrections matter because Jupiter is one of the fundamental reference points scientists use when studying giant planets. When astronomers discover enormous planets orbiting distant stars, they often compare them with familiar worlds in our own solar system. And Jupiter is the obvious benchmark. So improving our measurements of Jupiter can improve the way we understand planets that are thousands of light years away. But perhaps the biggest lesson from Juno is that Jupiter is far more complicated than the simple diagrams we learned in school. Its magnetic field isn't a neat, perfectly symmetrical structure. Instead, it contains a complicated network of magnetic features, with major differences between the northern and southern regions. That tells scientists something important about what is happening deep inside the planet. The deeper they look, the less Jupiter resembles the simple gas giant portrayed in textbooks. The same is true of its atmosphere. From Earth, Jupiter looks like a beautiful ball covered in colorful clouds. But those clouds are only the visible surface of a much deeper system. Juno has revealed atmospheric structures extending hundreds of kilometers beneath the visible cloudtops. What looks smooth from millions of kilometers away is actually a violently dynamic world. Then there are Jupiter's poles. Juno has spent years studying the enormous cyclones surrounding Jupiter's polar regions. Unlike Earth's hurricanes, these storms don't behave like isolated weather systems that form, move, and eventually disappear. Jupiter's polar cyclones can remain tightly organized around the poles, interacting with neighboring storms in ways that have no perfect equivalent on Earth. Some of these storms are enormous, large enough to dwarf anything we experience on our planet. Their movements, collisions, and interactions give scientists an entirely new laboratory for studying atmospheric physics. And then there is Io. Io is one of the most volcanically active worlds known in the solar system. Its surface is constantly being reshaped by volcanic activity driven by enormous tidal forces. Juno has combined microwave observations with infrared measurements to study heat beneath Io's surface. The results are helping scientists understand how volcanic material cools and how heat escapes from the Moon's interior. Io is essentially rebuilding its own surface again and again. And then Juno delivered another surprise, not through a particle detector or a magnetic field measurement, but through a camera. During a close encounter, Juno captured a remarkably detailed view of one of Jupiter's small inner moons. The image revealed surface details that help scientists understand Jupiter's faint ring system. That is especially interesting because some of Jupiter's moons contribute material to those rings through dust created by impacts and surface processes.